Well, hello everyone, it's the 7th episode in the Sensory Ecology series, and today we're going to look into... Oh, don't tell me. He's come back for another go? Right, now I'm really going to give him what he deserves. Ha ha! Take that! Take that! Take that! And that, you little piece of shit! Oh, I'll get you for this! Oh, you, how dare you take over my show! You little swine! You little piece of... Oh, I tell you! Oh my God! Oh, this... Benito!
Oh, hello, Major.
Oh, for goodness sake! I only came in here to look for my trousers! Goodness gracious! Can't do anything these days! Hello everyone, it's the 7th video in the Sensory Ecology series, and today we're going to start looking at arguably the most important sense and the most well-studied sense as well, and that is vision. And because it's the most well-studied sense, we know so much about it, and because it's so different to all the other senses we've looked at so far, it's going to require quite a lot of background, and that's basically what this video is. We're going to look at the basic physics of light here, and almost some biochemistry as well, okay? So hopefully we'll get onto some biology eventually, but this won't be the most exciting video, I'm telling you now. So, vision. Now, pretty much all eyes that we know of see in the visible spectrum, see visible light. And that's partly due because visible light is the kind of light which transmits most easily through the atmosphere, right? But visible light isn't the only light there is out there. There's a whole electromagnetic spectrum. Okay, visible light lies around wavelengths of around 400 to 700 nanometers. Longer wavelengths, and you're going into the infrared, and that's basically going to be the topic of the next video. You'll see that's slightly different in a way, but we won't go into that. And then if you go on the other side, shorter wavelengths than visible light, then you get into the ultraviolet. Now, some animals can see in ultraviolet. They have special ultraviolet photoreceptors, but we don't, clearly. So most of life is in the visible spectrum because either side of those wavelengths, they don't transmit very easily through the atmosphere. So, I mean, they're not here on Earth anyway, so we won't be able to... What's the point in seeing them? Right? Okay. Now, light is a difficult one to get your head around because it can be thought of as a wave, but at the same time it can also be thought of as a particle, little packets of energy called photons. Okay? So we have what is called a wave-particle duality. Sometimes light behaves as a wave, sometimes it behaves as a particle. So it's a bit complicated. Now, if we think of it in the wave form, an electromagnetic wave, as the name suggests, consists of an electric side and a magnetic side. So it consists of an electric field oscillating sinusoidally, yeah, and perpendicular to that, so at right angles to, you'd have a magnetic field oscillating sinusoidally. So that's what it looks like, but a lot of the time we're thinking of light in terms of particles, so photons. Okay, so you'll notice that I mix and match, I switch between the two different ways of looking at light throughout these next few videos. Another equation for you, this is quite an important equation actually, and that's E equals hv. E is the energy of one photon, and the energy of one photon can be worked out by multiplying the frequency of the electromagnetic radiation by h. Now h is the Planck's constant, and that is equal to 6.62517 times 10 to the minus 34 joule seconds. Okay? So that basically means you've got a decimal point with 34 noughts and then 6.62517. Okay? That makes it one of the smallest numbers in nature. Okay? It's quite ridiculous. Now, you can also express that equation as hc over lambda because the frequency of any electromagnetic radiation can be worked out as the speed of light over lambda. And the speed of light is 3 times 10 to the 8 meters per second. Okay, so 300 million meters per second. So every photon of light of a particular wavelength has a particular energy. Okay? Now, irradiance then, that's the amount of photons, you can also call it as the photon flux, okay, hitting an area in a particular time period. So it's measured as the number of photons per meter squared per second. Now the threshold for us is about 10 to the 10 photons per meter squared per second. So that means our eyes operate over 10 orders of magnitude per irradiance. Right? And we can categorise different types of irradiance into these three words here: photopic, mesopic and scotopic. Where photopic is really bright, so that's bright sunlight. Mesopic is sort of twilight light, yeah, sunset, that kind of thing. And scotopic is basically starlight, quite dark, okay, not much irradiance there at all. Okay then, so that's physicsy part of it. Now we need to know what happens when light interacts with matter, because it needs to do that for us to see things, okay? It needs to interact with things in our eyes. So at a very basic level, this is what happens. So remember, you've got photons, these packets of energy. When they hit a molecule, it will give that molecule some energy. Now remember, from basic GCSE physics, molecules are made up of atoms, and those atoms are made up of electrons in their own shells orbiting the nucleus of that atom. Right? When those molecules absorb energy, then that will give those electrons enough energy to move up to another shell or energy level, right, or energy state. Now if you give them enough energy, that could be enough energy for the electrons to completely leave the molecule, in which case we call it ionized, okay, that's ionization. Incidentally, I was talking about ions last time and I realised after playing it back, it sounded like I was saying iron, the metal. I wasn't saying iron, I was saying ion, I-O-N, right? If the energy isn't strong enough for an electron to leave an atom, it could cause that electron to jump back down to its original energy state, and in that case, it would result in light being released. Okay, so you'd get fluorescence there. It could also cause the molecule to change shape, cause it to react with another molecule, or it could cause it to break apart completely. Okay, so these are all things that could potentially happen. That's at a very basic level. We'll look at it in a bit more detail in a bit. Right? Now, some more spectroscopy kind of terms here. Transmittance is what we call the I, so that's the intensity or the irradiance coming out of an object, divided by the intensity or the irradiance going into the object. Okay, so the transmittance of an object is that ratio, which is pretty simple really, because imagine if you shine light through an object, nothing comes out the other end, so then you get zero divided by anything is zero, so you'll have zero transmittance. That's pretty obvious. You also have this thing called absorptance, okay, which is a bit of a funny word. It's given the symbol P for no apparent reason, I don't know. And that is basically the opposite of transmittance. That's 1 minus the transmittance. So it's basically the whole, everything, take away what has been transmitted. Okay, so that's quite obvious. Now, absorbance is a logarithmic scale. So that's why it's equal to minus log to the base 10 of transmittance. Now the absorptance of a chemical differs depending on the concentration of that chemical and the wavelength of light that you're putting through it. Okay, so let's say you have put a red filter, you've got a red filter. Then light passing through the red filter will have a greater transmittance at longer wavelengths, because red colour is longer wavelengths. And vice versa if you use a blue filter. If you use the green filter, then you'd get a peak in the middle somewhere, because that's in between red and blue. We'll have a whole video dedicated to eyes later in the series, but for now, we're going to be talking about those photoreceptive pigments, which is universal really to all eyes. But basically there are two types of photoreceptor in our eyes, in the vertebrate eye anyway. There's rods and then there's cones, right? Rods are just receptive to light in general, okay? So they're very good. They're the kind of photoreceptors you'll use if you're trying to find your way around somewhere in the dark, okay? They're just light receptors. The cones are what give you your colour vision, and like I said, we'll have a whole video on colour vision later in the series. So there are three types of cones. There's your red cones, your blue cones, and your green cones. Yeah? And using those three cones, you can build up all the colours that we see today, okay? Unless you're colourblind, okay? In which case, that's a bit awkward, isn't it? And these rods and cones have photoreceptive pigments, and these can be found in the transmembrane bilayer, okay, of those cells. And it turns out that these pigments are what we call G-protein coupled receptors, which is a bit of a mouthful, but if you know your cell biology, you'll know that they're actually quite common. And these G-protein coupled receptors have 7 transmembrane helices. They're called alpha helices, so they go through the cell membrane. And they often have what we call non-polar amino acids in them. Now the protein part of that pigment is what we call an opsin, right? It's coded for by opsin genes, okay? So that's what makes up these alpha helices. Also on that molecule is what we call a retinal attachment site. Now what the hell is that? Well, that is where the chromophore sits, okay? So a pigment is made up of the opsin, those 7 transmembrane alpha helices, and a chromophore, which absorbs the light, okay? And that chromophore in this case is retinal. And it's that retinal, as the word chromophore suggests, it's what interacts with the photons coming in, okay? And it's the rest of the opsin which tunes the energy to a particular colour. So the whole rest of the opsin sort of refines it, points it in the right direction, if you like. But it's the retinal that first absorbs those photons. Okay, so it's getting a bit complicated now, isn't it? So to summarise then, these photoreceptors have pigments, and these pigments are GPCRs, G-protein coupled receptors. The chromophore attached to the opsin part, so that's the protein part of that pigment, absorbs the light. Okay, that's what the chromophore does. That's usually retinal, and it's the rest of the transmembrane helices that sort of tune that to a particular colour. Okay, that's what the protein part does. So if you look at these photoreceptors, what you find is that at the ends you get sort of stacks of discs. Okay, and that's perfect because that increases the volume for all that visual photopigment, right, which is what we need. Because remember, these pigments are found on the membrane, so if you have these little discs, that creates more membrane, more surface area for those pigments to be found. Okay, another thing that's interesting is that if you look at rods and cones, you'll see that they have a remnant cilium on them, which suggests that rods and cones share a common ancestor somewhere, and that common ancestor had cilia. And these cells also have a lot of mitochondria, because presumably it requires a lot of energy to keep producing this photopigment. A single rod cell has 100 million molecules of pigment. Now if we look at where all these GPCRs came from, it seems to suggest that they have a common ancestry as well. Although that's a little more tricky to look at really, because these proteins, as you know from A level, have a primary structure, then a secondary structure, then it can be folded over into a tertiary structure and even a quaternary structure. And those structures are specific for particular functions. Unless we can sequence a whole protein, it's difficult to work out relatedness, but there does definitely seem to be strong signs that these proteins all share some sort of an ancestor. And we use this thing called X-ray crystallography to work this out. It's all very fancy. So retinal then, getting more into the biochemistry of that, that's the chromophore, remember, and more specifically, it's an aldehyde of vitamin A1. Okay, now your body can't just produce vitamin A1, it needs to be consumed. Okay, so that's why it's very important to eat your greens and stuff, so you can get all this vitamin A1, and that improves your vision. Now there are animals which use the aldehyde of vitamin A2, and these are called porphyropsins, and they're found in some fish. Okay, that's a bit of a random fact for you. So photon capture then, what exactly happens? Well, as we talked about earlier, when a photon hits a molecule, it can have several different effects. Okay, and in this case, it results in a change of structure. So the retinal is changed from a cis isomer into a trans isomer. Now that really is going into some real chemistry here. If you remember A-level physics, you may remember stuff about cis and trans isomers, but to put it simply, they're different forms of the same molecule. Okay? The cis isomer is exactly the same as the trans isomer, but the way that those atoms within the molecule are arranged in space differs. Okay? So it's a change in shape basically. And then once that happens, the trans isomer can go back into the cis isomer relatively quickly. So you've got your three pigments then. Obviously these cells are quite small, so in your retina, which is where the photoreceptor cells are, then when light hits, it'll inevitably touch one of the receptors. Okay? So rod cells, for example, aren't fussy. The cone cells, of course, have three colour channels. So, for example, one which responds to red light, absorbs blue and green, but is inhibited by red light. So that means red light is reflected back, so that's why we see something as red. As you can see on that graph, we have something called a lambda max, so that's the wavelength of peak absorbance. Okay, so that's the wavelength where it's more efficient, if you like, more light is absorbed by the pigment. Now the first thing to take into account here is this thing called univariance, right? So univariance is that there's an absorbed photon has the same effect in transduction regardless of the wavelength. So it's not that a wavelength which isn't lambda max has a different effect on the photopigment to the one at lambda max. It's just that the absorptance of a photoreceptor cell differs with the wavelength. Okay? So that means the sensitivity of a photopigment is determined mostly by P, which remember is the symbol for absorptance. So the photopigment itself isn't that fussy, right? It's the absorptance of the photoreceptor which gives you that curve. Okay? Right, neuro stuff. So eyes are a bit weird, okay? Because usually, if you know your classic neuro, you'll have something at a resting potential, and then you'll get an impulse, which causes a depolarization of the membrane due to the opening of sodium channels usually. Yeah, classic neurobiology this is. So sodium channels enter the cell causing depolarization, so the inside of the cell becomes more positive in electric potential. Oh no, that doesn't happen here. So in this case, the resting potential is about minus 30 millivolts, but after light hits it, after transduction basically, there's hyperpolarization. Hyperpolarization means that it gets more negative. And that's of course due to the movement of ions. Protein channels opening, letting ions outside, in this case, of the membrane, making it more negative. Okay, likely to be sodium and potassium, those kind of things. Okay. Now, the amount of hyperpolarization is dependent on the irradiance, okay? So we're bringing it all back now. So the greater the irradiance, the greater the hyperpolarization. And that's something which our brains can then deal with. And of course that can go down neurons. When it reaches a synapse, it causes a release of neurotransmitter, and then it carries on and on and on. Now, that's when it gets to the neural process. But we've kind of missed a gap here. We've gone from photon absorbed by the photopigment, causing the change from cis to trans isomer. But then how does that result in neural impulses? Well, the transduction process is very, very complicated. And if you know your cell biology, then you'll probably understand all this about GPCRs and what they result in. But to put it briefly, basically, this whole transduction process acts as an amplifier. Okay? One molecule is activated by the photon. That goes on to activate other molecules, which goes on to activate other molecules, then it breaks down another, and blah blah blah, basically amplifying the signal throughout the cell. And more specifically, I'm going to read this out here because I have terrible trouble remembering names. So, the GPCR is activated. That activates a molecule called transducin, right, which then activates a molecule called PDE, which helps to break down CGMP, right? God, these are first year memories coming back. And this has an effect on the number of open CGMP gated ion channels. Okay, so there's a whole lot of cellular machinery going on here, but to be honest, we don't need to worry too much about that. Now, it actually takes something in the space of seconds for a photoreceptor to repolarize, which actually is quite slow compared to the things we've seen before. Okay. Now, to get a good idea on how a photoreceptor works, you have to plot something using a V log I function. What the hell am I going on about now? So let's have a look at one, shall we, and see if we can understand it. So you can see that it has a sigmoidal shape which eventually plateaus, right? So any photon flux above where it plateaus will not be coded for, okay? It won't be sent to the central nervous system. So basically this is a sensitivity curve, and it can be moved horizontally through the process of light adaptation. So this is an example here, right? This is all very neat then, because that means the transduction system can be regulated so it can work over different orders of magnitude, depending on what conditions you're in. For example, in the dark you'd want a greater amplification of the signal because the light isn't that great in the dark, so it'll allow you to see better. So your eyes have got all these sort of tricks to help you see the best that you can possibly be. And this is all regulated using calcium. And that's very useful because photoreceptors normally work over 3 to 4 orders of magnitude. Adaptation allows you to shift that V log I curve to the left or to the right, depending on where you are, to increase your sensitivity if you need it. So if you walk into a dark room and you want to see things, or if you walk into somewhere really bright. Now, we've talked about using psychophysics to determine what animals can perceive before in this series already. And these are people that really pioneered psychophysics, Weber and Fechner. And they realised, well, Weber, this is Weber's law, and he found out that this equation was true, right? So delta I over I equals a constant. So what does that mean? Well, that means if you have a quantity, so I in this case stands for intensity, if you change that quantity, so that's what delta means, delta always means difference. If you expose someone to a constant stimulus and gradually decrease or increase the intensity, after a specific point, they'll notice there's a difference, okay? So basically it's all in relation to the amount of light you had to start with. Now, this has nothing to do with light, but I've got some cotton buds here, because I'm a big fan of cotton buds. I can't go anywhere without my cotton buds, quite frankly. I once spent a week without cotton buds, and it was honestly the worst week of my life. But anyway, that's not the point. Here are some cotton buds, right? Now what I'm going to do, this is going to be great fun, I'm going to continuously show you my cotton buds, right? And then you've got to put your hand up or do something when you notice that there's a difference in the number of cotton buds I have in my hand. Okay? Sounds simple enough? Obviously, I mean, I can't listen to you, I can't interact with you in any way whatsoever. So this is a completely pointless exercise, but let's do it anyway. Here we go. I mean, come on, I'm not going to kid you now. Hopefully by now you've noticed that the number of cotton buds in my hand was decreasing, right? Okay, you don't have to be a genius to work that one out. And I have to excuse me for a moment. Oh, lovely in yellow, look at that. Anyway, let's carry on. So that's the point then. So you can use that on animals to test, if you know, by measuring their responses or whatever, when they perceive a difference in the stimuli. And this proves this equation because let's say that constant was, I don't know, 0.1, okay? So that means if you had 100 cotton buds, you notice a difference when 10 were taken away, yeah? 10 divided by 100 is 0.1, right? That's simple. So that means if I had 10 cotton buds, you'd notice there's a difference when 1 is taken away, because 1 divided by 10 is 0.1, same thing, right? So that is, and that was displayed a lot more mathematically by this guy called Fechner, who said that dP is K times ds over S, where dP is the actual threshold of perception, and K was the proportionality constant. So it was sort of looking into Weber's law in a bit more detail and dissecting out the different parts. Okay, so that was quite interesting, and I'm sure we'll come across psychophysics later when we look further into vision. Okay, that's me done for today. Next time we'll look into a weird type of vision, one that we can't do, that of infrared perception. And you'll see that a lot of the things that we've talked about today don't necessarily apply. You don't have to see with your eyes. Right, that's a good cliffhanger to leave you on, but for the moment, see ya.